Point 2, talking about the standard normal distribution. Okay, so we're going to start with, we can compare any normal distribution to any other normal distribution because in our eyes, they're the same if we just compare them in their own standard deviation, sigma, and their mean, mu. So to get the standard normal distribution, we essentially convert the entire distribution to z-scores so that the mean will be 0 and the standard deviation is 1. So the notation will look like this. It's normal with mean 0 and standard deviation 1. It's the standard normal distribution. So to do that, we have to standardize it, aka we're going to get some z-scores. So if we convert an entire normal distribution to z-scores, I want to emphasize the entire distribution has got to be normal. Otherwise, this won't apply. We can only compare normal distributions to other normal distributions. So if we convert them all to z-scores, or we standardize them, let's say, which means you just subtract the mean and divide by the standard deviation. So the new mean would be 0, and the new standard deviation would be 1. So if we do that, we can compare any normal distribution through their z-scores. We did the Babe Ruth example. We were able to compare different distributions of home run hitters because they were all normal. So we convert them to z-scores, and we just said who had the highest z-score, who was the furthest above their mean. We compare any normal distribution that way. Okay, so let's title this distribution here. So this is normal with mean 0 right here in the middle and standard deviation of 1. Mean 0 and standard deviation of 1 because we standardize all the values. Subtract the mean, divide by standard deviation. So the standard deviation is 1. So for each individual in the distribution, how do we get that? We took every single person, subtracted the mean. So the distribution now would have mean 0. If you subtract the mean, you know if you subtract values, it affects the mean. So now the mean would be 0. We divide by the standard deviation, so the standard deviation is now 1. So let's talk about the standard normal table, the piece of paper you got in class today with all the numbers and digits on it. So it'll give you the exact probabilities or proportions for the areas under the curve. So we already talked about the 68, the 95, the 99.7. That's a general rule of thumb. This will find exact values for you. So for the first example, here's how I'm going to write it. The proportion of observations less than 0.81 for a z-score. So if your z-score is 0.81, you look over here, 0.81. It means you're 0.81 standard deviations above the mean. What's the percentage below you? So what's the proportion of observations that are below you? So essentially we're going to look for the percentile here. Okay, so let's take a look at that table. So we got a table in front of us. How do you read a z-score of 0.81? So I'm going to zoom in here. If you focus on the outside columns, here's all the z-scores. So z, 0, 0.1, 0.2, 0.3. We're going to go down to 0.81, but this column here only goes to 0.8. So z is 0.8. So if you want 0.81, you have to map it over here. Here's the grid. So 0.8, and then look up top. There's 0.01. So if I combine those two by looking at the 0.8, and I want 0.81, so 0.8's there, and then the extra change that's left over, the little bit behind that, the 0.1, that's there. So where do those match up? Where do those line up? So 0.8 goes to here, that's how you read it. So that's our percentile, that's our percent right there, 0.791. Okay, so while we're looking at the table, I want to ask you a couple other questions. Let's say I want to look for a z-score of 1.92. So what about for a z-score of 1.92? Let's surf down the z-scores here. So there's 1.0, 1.1, 1.2, 1.3. So there's 1.9. So if I want a z-score of 1.92, I got 1.9 here. I'll circle that. And then as far as the column goes, the change, right? The little pieces that's left over. 0.00, 0.01, 0.02, in the hundredths place. So if I want 1.92, I'll circle the 0.02. Where would that meet up? Right at 0.9726. That's if I wanted a z-score for 1.92. Okay. Let's try one more. How about a z-score of negative 2.37? Okay. So if you look at this table, the z-scores are only the positive ones. But this table has a backside, so let's flip it over to the back here to the negative z-scores. And I'm looking for, let's try negative 2.97. So I'm scrolling up here, I'm on the negative side. So here's my z values, negative 2.9. Okay, so I'll circle that one. So negative 2.9, and then I want negative 2.97. So let's go up top here. I got negative 2.9, so I know I'm in this row, and then corresponding to the 0.07, the leftover hundredths place there. Come on down, let's go ahead and map that out. So there's that 0.07. Looks like we're at 0.0015. Okay, that was just a little extra practice so you get used to reading the z-scores on the outside and then the percents or the percentiles on the inside. And just to further illustrate what's going on here, so the z-scores, I'll go green for those. The z-scores are on the outside, so you can map them out on the outsides here. So those are all the z-scores in green. Z-scores. Okay, and then on the inside, I'll go pink for this one. That's all the percentiles, the percentages that are less than those z-scores. So everything in here, everything in there, those are all percents. Okay, so that's how you read it. Here's how you map it out. If you want a z-score, map it out over here, up and down this column and this row, find the corresponding percent in here. So that's just a general overview. So back to the notes here. If I want the proportion of observations, or the percentage of observations that are less than a z-score of 0.81, that's this region over here. So I can shade that. So I shade that. It's already been shaded actually, but I just shade right over the top of it. It's kind of nice. Percentage less than that, we looked up in the table, 0.791. So you could say that it's in the 79th percentile. So this is equal to 0.791. So instead of just using the general rule of thumb, the 68, 95, 99.7, we're going to be able to calculate the exact percentages instead of just estimating. So first thing we're going to do when we go through and we'll calculate these, we're going to actually draw a normal curve. So you're going to get practice actually drawing these curves nice and symmetric. Then you're going to shade the area that you want. So that interval, whether it's above or below, you're going to shade the curve. And then you're going to perform the calculations, and you're just going to show your work. Okay, so our answer for that one, 0.9706. And that should seem about right, just based on the area of the curve that we shaded. Okay, another quick practice one before we jump into the guided problems here. What if I want the proportion of z's less than negative 0.63? So that's 0.63 standard deviations below the mean. What if I want the proportion less than that? Okay, well, again, let's start with drawing the curve. And then first thing, smack dab in the middle, you know you got the mean at 0. And then let's put our boundary here, 0.63. So negative 0.63, it's below the mean. And then I'm going to shade, so draw a line straight up, and let's shade below that. Shade below that. Okay, so what is that area? I would definitely say less than half. I'm not exactly sure. So again, let's grab the table. So I got to get back to the negatives for this one because it's negative 0.63. So if we look down here, negative 0.6 is there. So I'll go ahead and mark that, negative 0.6. And then 0.63, right there, right? That aligns with 0, 1, 2, 3. Now you can look up on your table, but obviously I'm limited now, so negative 0.6, 0, 1, 2, 3, that should be right there. So 0.2643, which makes sense. About 26% of the observations are less than that. Okay, so 0.2643, which means in gray there, what I shaded, that's about 26% of the curve, the area. Okay, so I'm glad we got a couple practice ones in. Let's go down here. We're still going to sketch and label a density curve, and then we're going to provide appropriate evidence for our answer. So our calculations, we're going to use the table. So the first one, part A, proportion of observations less than 0.54. So that's still a z-score. So that means your 0.54 standard deviation is above the mean. So what are all the proportions, or what is the proportion of observations less than that? Well, instead of talking about it, let's actually just sketch it out. So this is what I want to find. Proportion of z's less than 0.54. Hopefully you've picked up on this notation by now that I'm using. Capital P, and then parentheses, it's just z less than 0.54. Later on, that P is going to stand for probability, but for now, we're just letting it be proportion. Okay, so let's go ahead and sketch the curve. And then right there in the middle, let's put the mean. It's going to be 0 because it's a standardized curve still. And then for 0.54 standard deviations above the mean, somewhere in here, just an estimate, 0.54. And so let's sketch this, put a dotted line right to the curve right there so we can define our interval and shade everything below that, because that's what we're going to represent, the proportion of observations below 0.54. Definitely looks like over half, right? So let's go check out 0.54 on the table then. So I'm at the positive z-scores. Z starts here, 0.5 right there. So 0.5 and then 0.54. Looking this way, 0.7054. So if I can just map that out. So here's 0.5. I'm going all the way to 0.4. Right there. Where do they meet? Right in the middle at 0.7054. So I'm going to add that information. The proportion, my answer from the table is 0.7054. So everything we've done up to this point has been observations less than the z-score. What happens when we have observations greater than the z-score? So part B says greater than negative 1.12. So if you're at a standard deviation of negative 1.12, what's the proportion of observations bigger than that? Okay? So let's write it like this. Proportion of z's greater than negative 1.12. And let's go ahead and sketch the curve. Put the mean right in the middle. So negative 1.12 would be down here somewhere. So I've got it right there, negative 1.12. So if I'm looking for the proportion of observations bigger than that, let's go ahead and shade everything above it. Shade all the stuff above it. So just looking at this, it seems like a simple idea, like, okay, I'll just tell you what the proportion is. But our table only reads values to the left. So if we go and look up the value, the percent for negative 1.12 in our table, that'll be talking about this to the left. Well, then what do we do to come up with this part in gray? Well, you know the whole curve has to add to 100%. So if you could just tell me what was down here in the corner in the left, what this x is, if you could just tell me what that was, I could just subtract it from 1. Like, let's say this lower part here is 28%. Then I would just do 1 minus 0.28 to get this answer. Okay, so we'll still look up negative 1.12 on the table, and I'll tell you what this lower bound is, and we'll just subtract that from 1, and that'll be the answer for this gray area. So let's take a look at the table. For our negative z-scores, negative 1.12, so way down here at the bottom it's negative 1.1, negative 1.12, looks like it's 0.1314. So down here, 0.1314, this guy. So I just went from negative 1.1, and I went from 0.02 on the top where they meet, negative 1.12. That's our value. So what does that mean for our density curve? Let's take a look back at that. So that 0.1314 that we just found, that gives the area to the left of this negative 1.12. That gives the area to the left of this boundary, because all the values on the table are only reading to the left. But if I can just erase this x right here, get rid of that, and I'll write it in there, 0.1314. So that means in red here, I'm just going to shade it. The table only gives us stuff below, stuff to the left. So we looked up negative 1.12, and everything below it is only 13%, 0.1314, so about 13%. So that can actually tell us the answer for what's left over. If we don't have to be 100% total, we could just do 1 minus 0.1314, and that'll tell us what's in gray here. So here's the big idea. The proportion of z greater than negative 1.12, that's just 1 minus the proportion that's z less than negative 1.12, which is exactly what we just found in the red here. That's 0.1314, about 13%. And again, that's just because the table only reads to the left, but that's our way to get around it. We'll just do 1 minus the stuff less than negative 1.12. So that's 1 minus 0.1314. So what's the leftover out of 100%? 0.8686. So in general, if you want a proportion that's greater than a z-score, you can just do 1 minus the proportion that's just less than that z-score. We'll just subtract it away from the whole, and that'll give you the proportion that's actually greater than it. Okay, so for part C, we got another greater than question. What's the proportion of values greater than 3.89 standard deviations? So that's pretty far out there. So let's go ahead and get that notation down. Proportion of z greater than 3.89, and then get the curve down with mean 0 right in the middle there. So 3.89 is going to be way out here. If you're 3 standard deviations, almost 4 standard deviations above the mean, that's way out there, 3.89. And then just shade that little bit of tail that's left over there. So again, if we look up 3.89 on the table, the answer for that, the output for that, is just going to tell us the stuff less than 3.89, which we can still use that information, because if we know how much is less than 3.89, so I'll just put X there. If we know all this area, the stuff that's less than 3.89, then the leftover will be the stuff that's bigger than 3.89. So let's go to the table and take a look at that. So it looks like the biggest z-scores the table even cares to bother about is 3.4, maybe 3.49. So that means the area under 3.49 is 0.9998, which is almost 100%. So if we're talking about even bigger numbers, we're talking about looking for z less than 3.89. That's got to be approaching 1, so maybe 0.999999, so on and so forth. But for our purposes, that's essentially 100%. So now we just have to answer the question. If there's nearly 100% of the data below 3.89 standard deviations, what does that mean for percent of data above 3.89? If it's 100% below it, there's probably 0% above it, right? So if we apply the same logic we did in the last problem, the proportion above 3.89 would be 1 minus the proportion below 3.89. So 1 minus proportion of z less than 3.89, which we just found that to be pretty much 1. So if you think about it, we're talking about 1 minus something that's approximately 1. So what are you left with? The proportion of values above 3.89, well, if 100% are below it, it's approximately 0 above it. So that means 3.89 is pretty rare. That's way above the mean, and for all our purposes, that accounts for essentially 100% of the data below it. So there's 0% of the data above it. Let's look at the last problem here, part D. It's a little bit more intense than the other parts. So it's proportion of observations between 0.49 and 1.82. So those are our z-scores. So how do we represent that with our notation here? So we can say proportion of z's between 0.49 and 1.82. So I'm going to put the z smack dab in the middle. It's bigger than 0.49, but it's less than 1.82. So what's the proportion of z's in that interval? So let's draw the curve one more time. Put mean equal to 0 in the middle. And then let's get our boundaries marked off here. So 0.49, 1.82, and I want to know proportional observations inside this region. So I'll go ahead and shade that. Okay. Now, the table only gives us areas to the left. So it can't give us this specific distribution, right? It can't just give it to us right away, straightforward. So we're going to use a different method to solve this. We're still going to use the table, information from the table, but we're going to go about a different way. We can't just read it from the table. So if you have an idea in mind, I encourage you to just pause the video and try it and see if you can come up with it. Otherwise, I'm going to take a look at areas to the left. I'm going to start with 1.82. So what if I just found the area to the left of 1.82? What would that be? Covers almost all the distribution, it looks like. I would guess 90% or more. So if I can get all the stuff less than 1.82, that would give me a start. I know it covers mostly all of it. So maybe that gives you a hint as to how I'm going to go about solving this thing. So I'll let you get the proportion for this 1.82. I think it's actually 96% of the data is less than 1.82 standard deviations. Okay? So how can I still get back to that interval I wanted? Well, I'm going to start with blue there, proportion less than 1.82. Already got that shaded right now. And then what if I subtracted away everything less than 0.49? What if I could just delete all this stuff less than 0.49? Wouldn't I be just left with the interval that I wanted? So I'm going to use some color here. In orange, that's the proportion of stuff that's less than 0.49. I'm going to shade that in. So couldn't I just subtract that away? Because the table will give me that. If I look up 0.49 in the table, it will tell me the stuff that's less than it. So if we start with the big upper boundary, and then we subtract away the lower boundary, like this, if I start with z less than 1.82, all those values, and then subtract away the proportion of z less than 0.49, what are we left with? We delete that 0.49 piece, subtract it away, we're left with the original interval that we wanted. So if I actually put the percentiles down here from the table, 0.9656, a little over 96% for less than 1.82, and then subtract away that orange piece, that was 0.6879. That's exactly what we just did with this graph. So our final answer here, 0.2777. Okay, so I hope the colors made sense to you there. I'm going to take a step back and look how we got there one more time. So here's where we started, 0.49 to 1.82. What's the proportion of observations between there? Okay, so pretty much we just looked at this upper bound, z less than 1.82. Let's start there. We shaded everything less than 1.82. And then the idea was that we could simply just delete the stuff less than it. We could delete the stuff that was less than 0.49. So if we delete that, we're left with the interval that we want. We get the z-scores for those two pieces, because those we can come up with in the table. Those are z less than, z less than. That's exactly what the table reads. The proportion of values less than it. So that's what got us to our final answer of 0.277. Which should make sense, right? That's reasonable, 27% of the data in this interval right here. So it looks like if you need to find an interval, start with the big value, look that up on the z-table, and then subtract away the stuff less than it with the small value. Okay, so let's look at part E here. Proportion of values within 1.5 standard deviations of the mean. Well, from the 68, 95, 99.7 rule, we had 95% being within 2 standard deviations of the mean. What percent's within 1.5? So we're not going to use the general rule anymore. We're actually going to be able to calculate this. So let's draw I got a nice big normal curve for this one. Mean's equal to 0. 1.5 above and below the mean. So those are my boundaries. So I'm interested in, let's shade here, I'm interested in the stuff in between 1.5 and negative 1.5. It looks like a majority of the data, right? It's going to be bigger than 68%, but it's going to be smaller than 95%, just based on the rule. So now we're dealing with another interval again. So this is proportion of z's between negative 1.5 and 1.5. Proportion of values in here. We're dealing with another interval. Okay. So let's look at the upper boundary here, 1.5. Again, if I could just, I'll go in green here. If I could get all that stuff taken care of, I can get that on the table. Proportion of z's less than 1.5. I can get that one on the table pretty easy. And then I'm going to subtract away in pink the proportion of z's less than negative 1.5. So that was my lower bound, right? So if I could just delete this tail down here, I would have the interval that I wanted. So in pink there, if I could just delete the stuff that's less than negative 1.5, then I would be in business. So I can get both of these values on the table. I look at the table for 1.5, 0.9332. So that big green thing covered almost all the graph there. And then down here with the pink, 0.0668. Mine's not exactly drawn to scale, it looks like, but that's the lower end. So below 1.5 standard deviations. So if I can just delete that part. So I'm subtracting that off. I started with the green, and I subtracted off that pink piece. Now that gives me the interval in the middle that I wanted all along, 0.8664. So again, if you have an interval, it looks like we can just find the z-score, everything less than that upper value, proportion of z less than 1.5, and then just subtract away the proportion of z's that are less than the lower value, and that will give us our interval that we want. Okay, let's look at the next piece here. It says a distribution of test scores is approximately normal, and Joe's score is in the 85th percentile. That's pretty good for Joe. How many standard deviations above the mean did he score? So you may not know right off the top of your head, but it's going to help us to visualize it. So we need to go ahead and sketch the graph again. So what does this mean? The proportion less than Joe, right? The proportion less than Joe would be 85%. That's the definition of a percentile. So how many standard deviations above the mean did he score? Well, let's see. What's his z-score? Mean equal to 0, smack dab in the middle. I'm sure you're pros at drawing this curve by now. So this is a little bit different type of problem. Before I marked off z-scores down here on the axis, and then I just found proportions less than that. But now we're dealing with a percentile. So if he's in the 85th percentile, he's somewhere up here high in the distribution. But you know that he's above 85% of everyone else. So what does that look like if we shade it? Let's just estimate 85% somewhere in here, and I'll shade everyone else's below him. So this is the curve, the area of the curve I think is going to represent 85%. That's my estimate. Because he's in the 85th percentile, so he's above 85% of everybody else. So for me, my purposes, that represents 85% of the curve. So now the big question. What's the z-score he's at? What's his z-score? That he's so special, he's in the 85th percentile. So up to this point, we've been using that table to look outsides at the z's and then find the proportions or the percents on the inside. Now we need to go backwards. We need to look inside. There's only one 85% on the inside. Go find that 85% and see what the z-score is for it. So that's our next order of business. Look inside the table. Look inside the table values for 0.85 and give the z-score that goes with it. Let's take a quick peek at the table. Okay, so if you look inside of the percentages here, you notice kind of a pattern, right? 50% right here at 0. It's interesting. And then everything's increasing. So we're looking for 85%. So right here, very, very close, 0.8508. That's about as close as we're going to get. So if that's Joe's percentile, 0.8508, in the table you already know read stuff less than the z-score. So that's where he's at. what's the z-score that goes with that, 0.8508? So we just have to read the table backwards a little bit. The z-score that corresponds to it looks like 1 point, and go straight up from there, 1.4. So that would be his z-score that goes with 85%, 1.4. So if Joe's z-score is 1.4, what does that mean exactly? How do we interpret that? Joe's approximately 1.4 standard deviations above the mean. And so his z-score over here, that's 1.4. We just found it to be. So again, that problem a little different. We're given a percentage, a percentile. We want to know what's the z-score that corresponded with it. So we went inside the table, looked at those percentages, and then read outside to find what the z-score was. Okay, this is the last question we're doing in today's notes. We're going to do the serving speed example tomorrow in class. So in a normal distribution, Q1 is how many standard deviations below the mean? Okay, so that's going to require you to know what Q1 means, or what Q1 represents. If you recall from Chapter 1, that's the first quartile. So that's the lower 25% of the data, or you can think of it as being in the 25th percentile. So Q1, that's the lower 25%, or the 25th percentile. So again, we're really given a percentage here, and the question is how many standard deviations below the mean is Q1 in this normal distribution. So we're going to go percentage, and then we're going to find the corresponding z-score again. So let's get the curve out one more time. Nice and symmetric, means equal to 0, smack dab in the middle. And then I'm just going to estimate here and shade in the lower 25% of data. So that's going to be like my Q1. First quartile, lower 25%. And again, the big question we're trying to answer, how many standard deviations below the mean is this? So this boundary here for Q1, what's its z-score? How many standard deviations below the mean is it? Okay, well let's go find 25% in those percentages on the inside of the table and see what we come up with. So similar to the last problem, find 0.25 on the inside where the percentages are and give the corresponding z-score. So these last two problems we've been working backwards a little bit. So let's go take a look at the table. So I'm searching for percentage, 25%. You'll notice I'm down here in the negative z-scores, which should make sense to you based on what we just shaded with the lower 25%. Those would be negative z-scores, so below the mean. So for 0.25, 25% percentage, let's see, they're getting bigger, bigger, bigger. 0.2514, how about that, 25%. That's as close as we're going to get right now. Okay, so there's 0.2514. My question is just, what z-score does that correspond with? So let's read it from the inside out. So the first part looks like negative 0.6 over here. Negative 0.6. Let me erase this so I can see the negative better. Negative 0.6, and then it's not on my screen anymore, but if you scroll up, that's 0.7. So negative 0.67 is what the z-score is for 25% approximately. So we just found for a normal distribution, Q1 has a z-score of negative 0.67. It's the lower 25%. Has a z-score of negative 0.67. So Q1 is actually 0.67 standard deviations below the mean, to be more precise in answering the question. All right, that's all for this time. See you in class.